Welcome back to the world of kinematics and robotics. This is the second episode in the series, where in the first episode we originally covered some basics of vectors and trigonometry. We covered through some formulae and some identities, and then we also started looking at some basics of physics being looked at from vectors as well and how we use it. We looked at dot products, and in this episode what we will see is a lot more of some of the basics, and we'll also look at a clear understanding of vectors in 2D and 3D space, and then we will move on to closed loop kinematics, and we'll move on to Gruebler's criterion and degrees of freedom and everything. So just to continue from the first episode, I believe we have said about acceleration types, cross product, which we will see more of these things in today's episode. Principle of moments, we'll study planar kinematics. We will see all the way till about Gruebler's equation for this episode. It'll get way more involved as we go further, and I will be solving a lot of planar kinematics, and eventually we will get to 3D kinematics of robotic arms, serial robotic arms, which will fall under open loop kinematic systems. We'll get there when we talk about it. So let's dive in. So from the previous episode, we looked at how displacement vector was represented in the Euler form, and we do a time differentiation of the displacement vector, and we get two terms essentially. One we call it the angular velocity, and the other one we call it the linear velocity. Linear velocity actually tells us how the magnitude of that vector changes over time, and angular velocity tells us how the orientation of that vector changes over time. That's what, when we time differentiate the displacement vector, we get the two terms. So we also want to know about the different types of acceleration and how it is represented in physics and how we know it. But physics to vectors to essentially mathematics here. Let's look at what that really means. So if we time differentiate v vector here with respect to time, there are two terms here. So if we time differentiate that, it's going to get a lot more complicated. So the first term essentially breaks into two terms. The second term breaks into two terms as well. So when we simplify it further, we get four terms here. What these four terms really mean is that the first term with a theta double dot is angular acceleration, that is alpha, represented as alpha in general. The second term here is r theta dot squared or r omega squared. That's actually the centripetal or the centrifugal acceleration. The third term here is the product of the linear velocity to the angular velocity. That's actually the Coriolis component of acceleration. Wikipedia would tell you that it is a fictitious force or fictitious effect. The effect actually has some real truth to it in general. It's not truly fictitious. It exists because of inertia, and there's so many other reasons why that exists. It is important to note that this is how you can actually figure out where it comes from as well. You know what it is. And the last term is the linear acceleration of that vector. So the four types of acceleration here are derived. Derived meaning it's a derivative literally from the velocity vector. So it is to note that here. So we also looked at, we saw the dot product from a little bit on the previous episode, but let's actually, just to understand a little bit, I had mentioned that dot product is the algebraic sum of the multiplication of the coefficients. That's a little wordy, but let's actually bring that in expression to understand what it really means. If a vector A is given by a1i plus a2j plus a3k, and b vector is given as b1i plus b2j plus b3k, then a dot b, the scalar product, is given as each of the coefficients of I multiplied together and algebraically adding them to a2 b2 and then a3 b3. That's what it actually means. Something I want to actually specifically mention is vectors don't have a particular position in space. They don't have a fixed position actually. They have a position, but it's generally not mentioned even in your 11th grade, 12th grade, whenever you learned vectors. But I can't stress on this enough to understand why this is important. So let's actually look at an example, and I would like to do this in both 2D and 3D. So let's see, let's bring our workspace here, and that's the origin. Let's call that origin, and let's say I take a vector somewhere here in this point. Let's call that a point, and we call it OA. So that's 2 units in I and then 3 units in J. So OA is 2I plus 3J. Note that this is only in 2D first. We will see more of it in 3D as well, and understand why this concept extends in 3D as well. So let's take another point B somewhere here, and then we call it 5 times I and then 4 times J. Yeah. So from previous episodes and from concepts, we know that AB vector is OB minus of OA. So if you look at AB, is actually conveniently marked here. So it's 3 units in I and then 1 unit in J. So OB minus OA will have to be that. So that's what it is. And let's take another point somewhere in this space. Yeah, let's take it here. So let's take it. This is negative 6I plus 2J. So we're moving negative 6 units along the I direction, negative I direction, or 6 units in the negative I direction. That's what we should call it. And we're moving from there. We move 2 units in the J direction. And let's take another vector somewhere here. Let's take that one, right? Let's take that as D. It's 3 units in the negative I direction and 3 units in the J direction, positive J. So if you look at CD vector, OD minus OC will give you the same number. You see OA and CD are essentially the same vectors, but they are in different points in the 2D space that we see. So they don't have a fixed position. There can be multiple vectors like this. They can be all around the 2D space. I just want to emphasize that the vector here, 3i plus 1j, can exist anywhere. So they don't have a fixed position in space. This concept actually extends well into 3D space as well. So let's look at it a little bit. As I had mentioned, vectors in 3D also do not have a fixed position in space. So let's see what we can do here. So I'm going to bring, just for the depiction purpose, I'm going to use a different tool here. I'm going to use Python. Please do not get scared away that, oh, I have to install Python. I have to install different softwares and tools. It's going to be more hard. I don't, what if it fails? It's a failure point that many of us get stuck in. Do not worry about such things. They are just tools. It's more important to understand the concept of it. Even I, as an engineer myself, I have gotten stuck with this kind of a thought in my head, but it really doesn't matter. I can't emphasize on this a little more because sometimes the engineers that like to show off, unfortunately, there are many engineers like that. They just like to show off like, oh, we use Python, we use Jupyter Notebook, we use like the different visualization tools. None of that matters. It is important to understand the concept of vectors here. You can use any tool you want. You can use a 3D CAD software. You can use like something like SolidWorks or CATIA. There are many softwares. These are all softwares and tools. They do not at any point replace the concept of what core mathematics and physics is. So have the thought that these are only tools to represent your ideas and they are not actually what is required. It's very important. If you're a software engineer or if you want to be one and people test you on your on what languages you know, it's not bad, but it's also important to note that the concept is more important. Your algorithms and the way you form your ideas is more important rather than knowing which language, right? So language is only a means of communication. It's a type of, it's a means essentially. Language has nothing to do with intelligence. I can't stress on this enough. So for depiction purpose here, I don't want to digress too much. So for depiction purpose here, the software used here is Python. And I've used one of the tools for my advantage here. So let's take 2 points in the 3D Euclidean space. Let's actually do it differently. First, let's bring in a Euclidean space. So that's a Euclidean space where let's call the origin first. Let's call that point as 0. Let's bring in the axes. X-axis is pointing to the right, y-axis is pointing towards up, and z-axis is perpendicular to both. Understand that it is important I bring it in this way, and I've labeled it and colored it for my convenience, where x-axis is red, y-axis is green, and z-axis is blue. Is RGB. I'm just using that. So let's take a point A. So that's somewhere in positive x and then positive y, and it's in the negative z. So if A is positive 1, positive 4, and negative 2, OA is given as that. And let's get one more point, B. It's also in positive x, positive y, but further down in z, negative. So let's say OA vector is given as that. We know what OB already is. So AB vector, if you ask me, is OB minus OA. So that'll be that vector. So let's actually plot that the other one as well, like OB as well. So now we know what it is. So that vector AB is like that. Just for visualization, let me bring some planes here before taking another point. Okay. The XY plane, though it is in the red and the green, I have made it transparent blue because the Z axis is actually perpendicular to that, and that doesn't change. So I'm calling that XY plane. Let's bring the YZ plane where the X axis is red essentially, and normal too, and the ZX plane, it's the Y axis that's perpendicular. So let's call, not normal is what we'll call it. So let's take something in that space where I'm pointing right now. So let's take a point C. So, but yeah, let's take it here. So it's -7 in X, positive Y, and positive Z. And let's take another point D, also in the same space. But and CD we all know is OD minus OC. You see that both vectors CD and AB are the same. So as we saw in the 2D space, the same concept can be extended in 3D space. The vectors can exist anywhere in space. So it's the same vector, it's the same magnitude, and it's the same direction as well, but they don't occupy any fixed position in space. It's important to note this, and hence I'm just bringing this up. We will use more of this 3D Euclidean space in this episode as well as in future episodes. It's just to understand the concept that vectors do not have a fixed position in space. So moving away from the topic, let's look at cross product. We actually saw scalar product or dot product in the previous episode. There is a product called the cross product, and it is defined as, let's say, two vectors A and B. A cross B, where cross is defined as by that symbol, is defined as the product of their magnitudes multiplied by the sine of the angle from one to another. This is very important. The scalar product was only angle between two, and we actually figured out why it was in the previous episode. But in the vector product, theta is actually the angle from one vector to another vector. And here the n vector here, or n cap actually means it's a unit vector. So this n vector, by definition of cross product, is defined as a vector that is perpendicular to both A vector and B vector. So the cross product is actually perpendicular and it's away from a plane if A and B were in the same plane or in parallel planes. So let's look at that a little more, right? As I had mentioned, theta is actually the angle from A to B. And because it's from one to another, we know that it's not going to be commutative. Generally, this is referred to as a vector product. So like how dot product is a scalar product, cross product is a vector product. And the result of a cross product is a vector. So it's important to note that. Let's actually look. As I mentioned, the vector is actually the result of A cross B is always perpendicular to both A and B. And they don't have to be in the same plane. What does that mean? So let's, and I had mentioned it's not commutative. Let's see what it means. Let's bring up the, so I've mentioned here that A cross B cross A equals the negative of A cross B. Let's see what it really means, right? So let's bring our space. Yeah. If A and B are in a vector in the 2D space, and let's say they are in some form here, though it's the space here is 2D, but it's actually a 3D output. So if A is in one direction and B is another direction, though I've not marked the direction of theta here, it's actually A crossed with B goes from one to another. And the result of A cross B is actually perpendicular to both A and B. And N is a vector acting in that direction. N is the unit vector in that direction. So if I do B crossed with A, B cross A is negative. It's the same magnitude, but it's in the different direction. What does this mean? Let's look at it more in detail to understand what it is. And it's actually fun to look at it in 3D as well. So let's get to understand this a little bit more, right? So what does this actually represent? Let's take a space. I'm on purpose not making this vector aligned horizontally or vertically. So let's take a vector A. Let's take another vector B. And theta is the angle from A to B. This is important to note. A crossed with B is defined as modulus or magnitude of A multiplied by the modulus of B multiplied by the sine of the angle from one to another multiplied by the normal vector, unit vector to those two. How that direction is given is by a right hand thumb rule. So if you were to keep your right hand fully open and then the four fingers, your forefinger, middle finger, ring finger, and the pinky are all in the same direction as A. And if you have to curl the four fingers towards B, so A to B, that is the theta angle, then the direction in which your thumb is pointing is the direction of the result vector. It's very important that you understand it. If it is the other way around, where you have to go from B to A, you cannot curl your fingers the other way around. So your thumb, you have to flip your hand. That means your B crossed with A will go from B to A and thumb will start pointing downwards. So this is how we get the direction of the result. So we are seeing this in 2D, but as I had mentioned earlier, the A crossed with B, that vector is perpendicular to both A and B. But let's look at this in 3D because you can't really make this understand in 2D. So let's look at it in 3D. And as a note here, don't get scared. This is nothing. This is actually very easy. There are enough tools that will do this for you. You can get into the details of this, but if a vector A and B are represented in the IJK form, then the cross product is given by the expression here. So it's a determinant of this. I'm not going to go into the details of this because we will use this later, but it's just to understand that this can be done. All right. It's very easy. It's not that hard. It's very easy. So it's just simple multiplication and arithmetics. That's it. So let's look at it a little more in detail to understand what this means in 3D. So let's actually get to see this in 3D space again. So let's get a Euclidean space first, and uh, as usual, let's get the origin and let's get the axes lined up. So let's see. Let's take 2 points in space. Let's say somewhere here to here, maybe. Let's say I'm going to get the pointer from here to here. All right. Let's get a point A and get a point B. Give those coordinates, and then we'll form the vectors OA and OB. And AB vector is given as OB minus OA, so we get that vector. So let's get 2 points in the same space, another 2 points, and let's call that CT. Let's mark that vector as well. So the cross of these 2 points, note that they are in 3D space. They are not in any case in the same plane or parallel planes. They are at different planes. So the cross product is actually a vector that is perpendicular to both. Let's get rid of the origin so that we can see it better. So the cross product, when we do the determinant, what was seen in the previous slide here, is that. So what does that mean? Let's this vector is actually perpendicular to both AB and CD. So let's see what that is. So if you look at what you see here, I have plotted it such that it is from the middle of A, or not middle, but shortest distance between C and D, and then getting the perpendicular. That is how it is. So as vectors don't have any fixed position in space, it really doesn't matter. But for purposes of plotting, I have plotted it this way. So don't get taken away by, oh, it's 3D animation, I have to like figure this out, how to do this. You don't need to figure any of these things out. It just will happen easily. So don't worry about it, all right? So let's see what cross product really means in physics. See, in physics and in kinematics and classical physics, cross product is used for obtaining multiple things. So I'm going to give some examples here. Angular momentum of a particle is defined as the cross product between, let's say, where the object is rotating relative to an origin or a rotation axis to the linear momentum. So R crossed with P. What does this actually mean? Let's look at it in a different depictions. What you see here is a ball. That's, let's say that is a particle in the vastness of space. A ball is nothing, it's small. Angular momentum about an axis or a point of spin is given. It's not about the spin of the ball itself, it's the spinning about a circle there, what you see. So if the radial distance r is that, and radial vector is r vector, and if the momentum, the linear momentum is the magnitude is p, but the p vector tells you what direction it is. The angular momentum L is given as r crossed with p. And if an object is spinning about its own axis, right? So that is the angular momentum of an object. So that is spinning with respect to its own center of mass. Then it is given as the mass moment of inertia crossed with the spin velocity, the spin angular velocity, omega. So just make a note of what this means. Understanding this is something that we will put to use more in future episodes, but it's just an understanding of how cross product in mathematics is actually applied in physics as well, to understand the direction of angular momentum as well as magnitude of it, right? So it is something that to note. Another application is actually torque. So most often you've seen torque of an engine, torque of a motor, and they just give you a value. Actually, torque is a vector, it's not a scalar. So if you say, oh, the motor has a torque of like 20 Newton meters or 30 Newton meters, yeah, that's the magnitude of it, but in what direction? For example, is it spinning only in one direction? Is it spinning in a different direction? If so, what is the direction of spin? So we actually get that direction by actually knowing what the cross product vectors is. So of those vectors. So let's take a shaft that's spinning. Yeah, right here. If a force is applied tangentially to that disk, and the vector from the spin axis to the point of application of force is given by r vector, then r pointing in the four fingers and f is where how you curl the r vector into, and then the thumb points the torque direction. So this kind of tells you what it really means, and rf sine theta, and n vector is just unit vector. So it tells you the direction. So we do use applied vectors in physics, and these are some examples. We will use a lot of it in the future, but let's just make a note of this as for now. You can pause the video and understand what this really means. Now that we have seen some level of cross product in physics, torque, what we saw in the previous slide, is the cross product of the radius vector to the force vector, r crossed with f. And let's think about it a little more. We have actually applied torque in our basic physics classes in 9th grade, 10th grade, at least where I'm from in India. We studied this in our 9th grade. Principle of moments is what we will just see a little bit, and we will apply this a lot in our future episodes as well. Let's understand what it really means, just a crux of it. It simply states that if you take a lever and there's a load here and there's a load here, the sum of the clockwise moments is equal to the sum of the anticlockwise moments. That's what this states about the pivot. So that's what principle of moment states. And we've used this a lot in real life, at least where when there used to be simple sellers on the street selling vegetables, there's a physical balance that they hold, and they put mass, graduated weight on one side, and just we start loading the other side, and we know that the mass is the same on both sides. So that's how we know that you're buying a kilogram of tomato or a kilogram of some vegetable that you want to buy. So they are equating mass. So it's just very simply how a physical balance works, and it's how it's used to measure the mass of objects with known graduated weights on one side, and it's just measured on the other side. So this works on the principle of moments, simply saying the sum of the clockwise moments is the same as sum of anticlockwise moments. Here, the distance from one to another, that's equidistant here to here in general. So all they have to do is add a set of graduated weights here and then add vegetables here. And they know if they put 1 kilogram here, the vegetables also will weigh, not weigh technically, there'll be a mass of 1 kilogram. That's what it means. So we'll use this more, but let's to look at some physical examples of principle of moments, of course, using the physical balance to measure the mass of one side with number of vegetables or with how much ever vegetables you're buying. That's one example. It's the same principle of moments concept that is actually applied in even slightly complicated systems. Moving away from regular life, let's look at some real world example, right? The most common thing to notice is a car trunk. We almost use this every day if you have a car, generally. If you don't have a car, physical balance is something that I have seen in the past. So let's take a side view of a car and with its rear owner. This is just a depiction. It really doesn't, in truth, there's a lot more to this. I'm just making it as a depiction here. So principle of moments is simply applied here. If you were to provide a force here to lift, and this is actually a spring or a gas spring or a torsion bar somewhere here, whatever, how much is the force required? These things are all computed using just simple principle of moments. These are not highly dynamic systems. They are slow enough that you can make it quasi-statically done. We will see and implement this a little more in the future episodes as an example of what moments are and how you can, what it's used to compute, as I'm giving it here. Don't get carried away by, oh, this is pivot point, liftgate points. All of these are just simple. It's a legend on a graph. That's what it really means. So the force required on an actuator on a powered liftgate is just simply based on principal moments. It's fairly straightforward. So let me just show you what it really means, right? We look at details of this. We will model hydraulic excavators, what's the force required. We can even model some concepts of Tesla and stuff like that, right? It's Tesla Model X is something that I worked on. So we can discuss about that as well. So to give you an idea, so let's see. So if that's the center of gravity and that's the gravity vector, what it means is that if I were to, let's say, open this, and I'm just plotting the external surface here in the 2D view to say what happens. And if you were to open this, what are all the forces? You see that the actuator is actually moving in one direction. It's pushing the system out. And when I'm closing it, what happens? What is the moment that happens over this axis or pivot point, if you will? These are all things we will see more in detail. And these are all coming from simple vector math. Very, very simple stuff. We will discuss this more in detail in the future episodes. So we spoke about all of those things. Let's discuss a little bit about what degrees of freedom really mean. And it's important to understand this concept in general. Let's get our space, a 2D space. This is a 2D space. It's not a 3D space. The concept of this can be extended in 3D space as well, which we will go in detail. So let's take an object. So this is like an object, solid object, and then we'll see it is in 2D space, so it can move in the positive X direction. Let's bring that back. It can move in the positive Y direction. It can move in the negative X direction. It can move in the negative Y direction. So essentially there is a X movement and a Y movement. The positive and negative is still in the same axes, if you will, and it can move together. It can pan, and it can also spin about an axis that is perpendicular to the board, to the plane of the screen that you're looking at, right? It can spin in the clockwise direction as well as it can spin in the anti-clockwise direction. What does this really mean? So in 2D plane, if I take an object that can move in that direction, it can move in that direction. In 2D space, wherever it moves, it can be represented as a movement in X and movement in Y, be it positive or negative. It can do both at the same time as well, but it's a movement in X and movement in Y. That's 2 degrees of freedom. And it can spin as well about the plane that is, about the axis that is perpendicular to the plane of the screen that you see. So that's +1. So that's like 3 degrees of freedom. So that's what it means. So let's actually erase this a little bit and understand what that means. So an object in 2D space on a plane has 3 degrees of freedom. So this can be figured out, and there is a person called Gruebler who made this equation work. And the concept that we'll see in today's episode is all in 2D. We will see a lot of these examples in 2D, and then we'll scale it up to 3D as well. In concept, this can be spread in 3D as well. So let's actually bring an object here. So that I'm saying that this is a link. We'll call it a link, an object body. And we'll say this has 3 degrees of freedom. Let's actually bring another link. So that's 2 objects, and there are a total of 3 degrees of freedom. So in total, the system has 6 degrees of freedom. So that makes sense. If I bring one more object, if I bring another object, so essentially that the 2, so let's now calculate the number of degrees of freedom. There's 4 objects here. right? And each of them have 3 degrees of freedom. They can move in X, they can move in Y, and they can rotate about the axis perpendicular. So that's 12 degrees of freedom. But let's see what we can do. So I'm going to take just two objects. I know that object has 3 degrees of freedom. And I'm going to pin, let's say I'm going to pin this like that with a pivot, right? So what happens is, however object 1 moves, it essentially moves object 2 along with it. Object 2, by constraining or constrained with object 1, has lost its ability to move in X independently and move in Y independently. All it can do is just rotate about a pivot. So 2 degrees of freedom has been lost for one of the objects. So this particular system you see here, for the first object there is 3 degrees of freedom, and the second object, it used to have 3, but it now only has 1. So there is total of 4 degrees of freedom here. Let's do one more thing, right? Let me erase this equation expression here, and let's say, let me bring another pivot here, and I'm going to be grounding. When I say grounding, I'm going to call it fixed. So now you see there are technically 3 objects here. The ground is counted as object 1, let's say, and the first link is object 2, and the third link is object 3. The ground essentially has no degrees of freedom, so that's a 0. And then there is a first link, which is number 2 here. It has a degree of freedom of 1 because it's locked. And then there's one more link here, which also has lost 2 degrees of freedom. It's got only 1. So this system, total degrees of freedom here, I'll call it DOF. This is also called mobility, but it essentially is 2. So what it means is that if I want to define a system of links, I need at least 2 parameters that can physically define the system's position. That's what this really means. All right. So let's erase all of this and figure out a little more better way of understanding this, right? In plane, there is 3 times n degrees of freedom, because in plane there are 3 degrees of freedom. And if there are n links, they'll have 3n degrees of freedom. So if I have a link like that, have another link like that, that's 3 times 2, right? That's 6 degrees of freedom. But as we mentioned, I'm going to actually go ahead and draw it again. So now this has 3 plus 1, 4 degrees of freedom. But when I ground this, there's 3 links, like including the ground. So I'll call it 3 times 3 links. Then I'll say minus the ground, which basically lost all 3 degrees of freedom, minus there are 2 joints here which arrest 2 degrees of freedom each. So what does this mean? So 3 times 3 minus 3 So 9 minus 3 is 6. 6 minus 4 is 2. So this system has 2 degrees of freedom, as we had mentioned. So this is what it means. But there are different types of joints. We will see more of that in the next episode so that we understand loops better. The joints that lose 2 degrees of freedom are generally called lower pair joints. And then if they lose only 1 degree of freedom, they are called higher pair joints. The way in which it works is a revolute joint here constrains the movement in X and movement in Y. It only allows rotation in Z. What if there is an object that can constrain, let's say I draw a similar system, a ground and a link here that is pivoted. But let's say I draw it to the dotted line here. So it has a slot inside. And I draw a link that can move only like that. So the link is constrained such that it can move only in one direction like that, but it has lost all other degrees of freedom. So it has only one way in which it can move up and down, which means it has lost 2 degrees of freedom. This system also has only 2 degrees of freedom, one about that and one in that direction. So there are two types of joints in 2D space that arrest 2 degrees of freedom. But if I were to allow this to move in different directions, let's say in one more direction, I have the slot big enough where it can move like that as well and spin, then it's a different deal. So we will get to those joints definition more in the immediate episodes. So it's just to note that this is called Gruebler's equation. So 3 multiplied by whatever I had written earlier. Let me just bring that out. So mobility is given as 3 multiplied by the number of links minus a ground link, because that loses all 3 degrees of freedom, minus, if you're losing 2 degrees of freedom with n number of, or f1 number of joints, and then if you're losing joints that have 2 degrees of freedom, they've lost one, and we'll call those number as f2. This is defined as the Gruebler's equation of mobility. So we'll know more about this definitely, but it's something to note. So in 3D as well, this concept can be extended. Of course, 3-dimensional space has 6 degrees of freedom. We will know more about it and we'll learn more about it. Don't worry, these are all available online on an internet or whatever. You can just search for Gruebler's mobility equation of planar mechanisms and you'll get it, but something to note. So we will study a little more about closed loop kinematic chains. So what we saw here was open, but what if the last link is actually joining with the ground? What is required to define it? That's something that we'll learn. We learn about open loop kinematic chains. What we saw here was essentially an open loop one. And how does a mechanism form? Serial robotic arms, even in 3D, till they touch an object in the ground, are essentially open loops. The moment it touches, it can be defined differently. So it's something that we will learn as well. And in our series, most likely we will have only rigid body kinematics. That's what we will be studying. The deformation in the bodies themselves are not looked into. So it's something to note. Just to give you an idea of what all we will see in the next episodes, we will study in detail about closed loop kinematic chains and the types of joints, as I had mentioned. We'll study 4-bar mechanisms and their different inversions if we change the joints from a revolute joint to a prismatic joint, which moves only in one direction. What are the inversions? Some very common examples of 4 bars. We'll see vice grips, very simple stuff that you'll know. A single cylinder engine is a 4-bar inversion. It's a slider crank mechanism. There are names that people have given to these things. We'll see how door closes, door mechanisms. As we saw, liftgate, that's also a mechanism. So we'll study more about those things. We'll give and work out a lot more examples. We'll study about hood hinges on cars. There's multiple amazing mechanisms available online. We'll study some of those. Hydraulic excavators, we can see some examples of how they work. We can look at slightly more involved 4-bar mechanisms like walking mechanism of Theo Hansen, robotic rippers, boom lifts with multiple stages and timing links, how 1 degree of freedom, but it's a complex mechanism, how it works. We can study that. Let's say we look at a simplified Model X Falcon door and see how that works. It's a simple mechanism, but it's something to note. And we'll study open loop kinematic chains. More of a discussion rather than a deep dive in 2D. That's what I'll say. And then we'll study in 3D motion. We will have to extend all the knowledge that we learn in 2D. We will revisit some of our chapters and we'll study what it means in 3D as well. We can look at how objects move in 3D space. And then we'll solve some very simple examples like how a fridge door or a simple door in the house opens and closes, what that axis really means, how to define those and everything. We'll study about how to define rotations in 3D space. We'll study kinematics and stuff. It might be overwhelming now. These are all just for notes. Don't get carried away, but there's amazing stuff that we can learn. And it all starts from these simple vectors. So it's something to note. That will be the end of this episode. Please don't forget to like, comment, share, and subscribe. I will look forward to any questions on the comment section and I can help as much as possible. You'll be able to do a lot of what you see here on screen. These are actual vector and path planning that's happening with a planar elbow. And we will study a lot more of how to apply all of this in real life. Cheers.